by Paolo Pani, talking about topological stars and magnetized black holes.
Okay, thank you very much. Thanks, Nick and Josi, for the kind invitation. It's always great to be here. So since this is a workshop, I decided to talk about some work in progress. So everything that I'm going to say is unpublished. And fortunately, I'm presenting this because I just discovered that there is also another group working independently on this field, and I think that Giorgio Di Russo will present some related result on Friday, I believe. So yeah, I'm presenting some ongoing work and project done with Alexandru Dima, who's, oops, is it working? Do you see something? I don't. Oh no, okay, it's this other one, sorry. So Alex Dima is sitting over there, and Marco Melis, who's a PhD student in Rome, I think is attending online. And well, this paper will be hopefully out soon within a couple of weeks. So one of the upshot is that we are starting the full linear stability of topological stars and magnetized black holes, these solutions that Pierre and Ibrahim proposed a few years ago. One of the upshots is that I'll discuss their signatures in the quasi-normal modes and in the time response and compare them with those of a black hole, and this is one of the pictures I will discuss later on. So the now this is really not working. Let me see. All right. So this is the outline. Well, I will first give some motivation. How do I see this? Ah, it's off. No, it's on actually. It's okay. I can change it through the keyboard. So one of the motivation is to start studying the dynamics of, well, possibly black hole microstates, and I think that after Helvi's talk this morning, the motivation is pretty clear, and also the challenges. And because of that, I will start with a theory, in particular 5-dimensional Einstein-Maxwell, and in particular also its 4-dimensional compactification, because we like to do things in 4D usually. And then I'll discuss very briefly the background solutions in this theory, magnetized black holes and topological stars, present their full linear perturbation analysis in the frequency domain and in the time domain, and I'll discuss a few analogies and differences. If I have time, hopefully, I will also present something sort of tangential but still interesting, I believe, which is black hole spectroscopy in Einstein-Maxwell scalar theory, which you will see has something in common. Okay, so the motivation, broadly speaking, the main motivation to me at least is to try to isolate certain key aspects of the fastball paradigm, the fastball program, while keeping it sufficiently simple that we can do computations. And in this context, we know that at least certain very coherent microstates involve smooth geometries without an horizon. And upon compactification, these geometries involve gravity, GR, coupled with a bunch of gauge and scalar fields. So we want to keep this feature, and in all this paradigm, a key aspect is the role of higher dimensions and non-trivial topologies to prevent these solutions to collapse and form a black hole. So this can be very compact, and because of higher dimension and fluxes, they can actually exist and survive collapse. However, well, there are, as you know, and many of you have contributed to this business, there are several of these solutions. The problem is typically they are very, very involved, and as Helvi remarked, beyond the existence of these solutions, very little at the moment is known about the dynamics. While the goal here is precisely to study the dynamics in this scenario, and I will focus on this particular solution discovered by Ba and Heidman a few years ago, so topological stars as a proxy to more complex geometries. And in this, at least in my perspective, this solution carries some of the key ingredients of this program. In particular, is a 5-dimensional solution, which asymptotically is Minkowski cross S1. It carries the same charge, the same mass and electric charge of say a black hole, but in the fifth dimension is compactified, and instead of having an horizon, down here there is, well, the space-time ends, and there is a bubble with fluxes that are necessary to for this bubble to exist, with finite sites here. So these solutions have been studied quite in detail in previous papers. Also, their geodesics have been studied quite in detail, their shadows, their geodesic properties, and also how also the dynamics of test fields on these geometries has been studied in the past. I'll discuss this in a moment. However, we are interested in understanding whether they are linearly stable in terms really of gravitational, electromagnetic, and scalar perturbations, which in these geometries are all coupled in a non-trivial way, and to compare their response to black holes. So this is the motivation. So let me introduce the F5D theory, and I apologize, there will be quite a lot of equations in this talk, but some of them are necessary to set the stage. So this is a theory, it's just Einstein-Maxwell in 5 dimensions, and this is the background solution that I will be focused on. It's particularly simple because it's spherically symmetric, but there is a magnetic field here whose charge is fixed in terms of 2 parameters, RB and RS, that we'll discuss later on in a moment. So it's a 2-parameter family of solutions which are spherically symmetric. Okay, for practical, but before it was working, no? I don't know. For practical, So for practical reasons, I will actually consider the 3+1 dimensional reduction of this theory. And so for the moment, I will not assume any y dependence. So y is the 5th dimension, the one that is compactified, this one here. Forgetting about this y dependence, the composition of the theory is the following. So the metric is decomposed in this way. There is the 4D metric, a dilaton, and then an extra gauge field. And the composition of the Maxwell field is, well, the 4D Maxwell field, an extra scalar field, and that's it. So if you count the degrees of freedom, of course, we have 2 + 2 + 1 for the gravity sector, 2 + 1 for the Maxwell sector, so in total there are 8 degrees of freedom. And as I said, all these functions and variables here are independent on the y coordinate. So the 4D theory, and this is well, a part of the computation that actually Alex also did, looks like the following here. So it's basically an Einstein-Maxwell dilaton theory, but with 2 Maxwell fields and 2 dilaton fields. So there is, well, GR, one scalar field, the other scalar field somewhere. I don't see, yeah, it's here, with no minimal couplings between the scalars and the 2 Maxwell fields. So there is the curly F and the standard F. These are the 2 fields. So these are the field equations, and even if they are ugly, I will show you anyway, because they might be useful later. So this is the GR sector, the Maxwell sector are these 2 here, one scalar field which is the couple from the rest, and then there is the dilaton couple to all this bunch of fields. In terms of the 4D theory, the background solution has this form, which is more familiar to those who work in 4-dimensional GR. So it's a solution that is actually singular. These Fs and Fb are basically 1 minus Rs divided by R, and the same for Fb, 1 minus Rb divided by R. So they are 0 at R equal to Rs and R equal to Rb. In particular, this metric is easy to see that is singular at R equal to Rb, which is where the space-time ends in 5D. As expected, because the 5-dimensional solution is perfectly smooth and regular, what happens is that the dilaton is also diverging at the same point. So this divergence, in a sense, is just an artifact of the 4-dimensional reduction. This is the magnetic flux. There is a charge, a magnetic charge, again, is a combination of Rs and Rb. And in this framework, so the 4D framework, these extra fields, the curly F, and whatever, Xi, maybe, the other scalar field, they are 0 on the background, so they're decoupled. So if you go back to the equations, because the background is uncharged against with these fields, these 2 equations here are completely decoupled from the others, just because they enter quadratically in the GR equations, because the background has 0 curly F and 0 scalar field. So this equation here, upon a redefinition of your scalar, is just the equation for the massless Klein-Gordon equation on this geometry. And this was studied in a paper by Pierre and collaborators, and also by Massimo Bianchi and collaborators. So I will not discuss this further, but it's essentially part of the full perturbation sector, one with a test scalar field. And same thing here, because there is no background curly F field, this equation actually decouples from the other, and this is the equation for a test massless vector field. This was studied in a couple of papers, I believe only for black holes, not for topological stars, but nevertheless, it's a test scalar field. I will instead focus on all the rest, so I will focus on this sector here, which is coupled because of the background to the dilaton and to the Maxwell field. So that will be my my stage. Sure.
I understand that in 5D there are no singularities, but in 4D you're saying there are. And also RB is bigger than RS in your...
I'm going to discuss this now in a moment, RB and RS, yes. But you are right, there are singularities. The point is also related with something that we were discussing this morning, because in 5D is regular, you know how to treat them, so you know the boundary conditions that you have to impose. Precisely about the parameter space, so... Oh, sorry, yeah, there is another question.
Yeah, just so just to be sure that I understand this, the perturbations that you're looking at, the perturbations that you're studying are just in the 4D spacetime.
So we are studying it in the 4D, but they come from the 5D. So a completely equivalent way to look at this problem is taking the 5D and do the standard Kodama-Ishibashi decomposition for the perturbations in 5D. And essentially there is a one-to-one mapping between
so there are actually all the modes of the 5D spacetime are present.
With y equal to 0. So no y dependence.
Thanks.
That's important, yes.
Because away from extremality, you're going to have a Gregory-Laflamme instability.
Yeah, I'm going to discuss this. I'm going to discuss this in a moment.
Yeah, and those are not in the field content.
Yes. Yeah, I'll take that into account later. Yes. Okay. Well, since we are discussing this, yes, it's important, but a big simplification is that the background is independent of y, so you can sort of parameterize as a Fourier mode the y dependence, and therefore, I mean, adding it is actually straightforward. Okay. So the parameter space is the following. This is the mass, the ADM mass of the solution. This is the magnetic charge, which is shown here. I mean, there are two parameters, but in fact, one set the scale, like the mass, and therefore there is just one physical parameter. The ratio, I'm taking here it to be the ratio between RB and RS. And in this parameter space, you have different solutions. So if RB is smaller than RS, you are here, and the solution is a black string in 5 dimensions with a magnetic field. So I will call this magnetized black hole in 4D. If RB is bigger than RS, then you are here, and the solution is regular. There is no horizon, because the horizon is at R equal to RS, and the spacetime ends at R equal to RB, which is singular in 4D, but regular in 5D. And, well, this solution has been called topological star. Unfortunately, depending on what you are interested in, these solutions exist, as you can see, in a parameter space in which the charge is different. So there are no solution with the same mass and same charge, black holes and topological stars, but at least there is this point here, around this point, in which they actually have essentially the same charge to mass ratio, and this will be important for what I'm going to tell you next. Going back to the Gregory-Laflamme instability, it is known that in fact there is this Gregory-Laflamme instability for black strings, And it's also known that even magnetized black holes are unstable against the Gregorian-Laflamme instability, and this essentially excludes all this region here when RB is smaller than 1/2 RS because of this instability. There is also a nice duality between black holes and topological stars that I will discuss later that tells you that because of this instability for black holes, there is also an instability in the opposite regime for black strings, for topological stars, which is here when RB is bigger than twice RS. So for the rest of my talk, I will actually consider only the region in between, which is what is in this inset here. So when RB divided by RS is between 0.5 and 2. Just one moment, I'll finish this. Within this range, which in principle is free of Gregory-Laflamme instability, topological stars can still be divided in two more kinds, depending on essentially their structure. What is called topological star of first kind are essentially star-like objects without an unstable photon sphere, while topological stars of second kind, they are more compact in a sense, and they have an unstable photon sphere, but also a stable one, which is crucial for their essentially linear response. And in fact, they reassemble the phenomenology of what typically in the literature, at least GR literature, are called ultra-compact objects. So from the point of view of GR people, of GR person, this model is actually very nice because in a single metric, a single solution, it interpolates smoothly, connects smoothly three regimes, black hole here, ultra-compact objects here, something that actually can be very similar to black hole at this point here, and then a sort of star-like solution for bigger values. Yes.
So at the kind of correspondence points between your magnetic stars and topological stars, so black holes and topological stars. You say that you can somehow have a smooth correspondence with the same charge and same mass. So what is this parameter RB? Can I understand it from a string theory perspective? Can I understand it from, let's say, something that depends on GS, for instance, such that in the end tuning like RB over RS would correspond to tuning over GS. Can I understand that?
I think that as in this picture here, very naively, RS is the size of the bubble, essentially. When this shrinks to 0, also the charge shrinks to 0, and you recover Schwarzschild black hole. Otherwise, you will have these sides, this bubble of a given size, and you need a magnetic flux to support it, which is why the magnetic charge is proportional to RB. I don't know if this answers your question.
Yeah, well, it was more about if I think about putting more gravity.
I see. I think yes, you should ask the guy behind you.
No, it's just changing the geometry a lot. So it's RB is really where the bubble is, and RS is really where the horizon is, and you change that.
But when you
But both move together if you change GN, like G Newton. It doesn't change.
okay. Yeah, you don't have a transition then. Okay, thank you.
Yeah, I get. Okay, I see your question. So they're both proportional to the mass, basically, right? So they, yeah. No, the mass. Yeah, this is another property I should stress more, which I like a lot, is that there is a universal scale, which is the mass here. So these solutions can exist actually. I mean, they can be bigger or smaller. Well, of course, there is a limit in size, but the mass is a free parameter, which is nice. It doesn't happen for many ultra-compact objects, like boson stars don't have this property. Okay. Okay, so this was for the background solution. Now, going back to the perturbation, another nice property, again, even if you don't like fastballs, but really are just a GR person, I think it's an interesting problem for linear perturbation from the point of view of linear perturbation theory. And the reason is that the background is even in the gravity sector and, of course, in the dilaton sector, but it's odd in terms of the magnetic sector. So this already is sort of different from what people are used to when, for example, studying perturbation Razer Nostrum, in which there is an electric field and not a magnetic field. And indeed, as written here, what happens is that because of the presence of a magnetic flux, there is a parity mixing. So what happens is that polar gravitational perturbations and scalar perturbations are coupled to axial electromagnetic perturbations and vice versa. And this is not what happens typically. And according to this, I would call type 1 perturbations precisely this, so the axial gravitational sector coupled to polar electromagnetic perturbations. And I would call type 2 perturbations the polar gravitational sector coupled to axial electromagnetic perturbations and the scalar. The scalar, of course, is part of the polar sector. It's obvious that type 1 starts at L equal 1 because there is no L equal 0 mode for gravity and for electromagnetic. Type 2 perturbation starts at L equal to 0 because even though gravity and Maxwell are not dynamical, you still have the scalar field. Okay? So the scalar L equals 0 sources actually gravitational and electromagnetic perturbations, but the latter two are not dynamical. Okay? But so this is the structure. As you might expect, type 1 is simpler to solve than type 2 just because there are less degrees of freedom. So here is the spherical harmonic decomposition. This is pretty standard, but just to give you an idea, I'm sure that most of you are familiar with this. So the idea is that you decompose the gravity sector for type 1. The gravity sector in odd spin 2 spherical harmonics, the electromagnetic sector in even spin 1 spherical harmonics, and that's it. So you have two functions. This is the Radio-Wheeler gauge for the gravity, and 1, 2, 3 functions for the Maxwell sector. For type 2, instead, you have the even perturbation, what are called typically Zerilli perturbations, which are 1, 2, 3 functions here. Then there is a scalar field, of course, 1 extra degrees of freedom, and then another extra degrees of freedom for the odd Maxwell perturbations. And the two sectors are decoupled, so you can see directly from the equations that because of the symmetries of the background, in particular because it's spherically symmetric and there is an even metric and an odd electromagnetic field background, the two sectors are completely decoupled, and each L is also decoupled because of the spherical symmetry. Okay, so here's some result. So first of all, it's pretty obvious that for L equals 0, so type 2 perturbations, you have an effective one-dimensional equation in frequency domain that you can always bring into this Schrödinger-like form with an effective potential. That's obvious because you have 1 degree of freedom. It's also obvious for type 1 L equal 1 perturbations, again, because you just have 1 degree of freedom, the electromagnetic degrees of freedom. It's much less obvious for type 1 L equal 2, 3, 4, etc. perturbations, because in that case you have 2 degrees of freedom, both gravitational, the axial one, and the even one electromagnetic. But it turns out, and this has been shown by Marco Melis in Rome, that you can actually separate the equations, so diagonalize the two equations, so you end up with two decoupled equations for these 2 degrees of freedom. And in general, so for type 2 L equals 0, type 1 perturbation of any L, you end up with equations of this form here, all decoupled from each other, which is very nice and easy to solve for. And I'm showing here the effective potential in various cases. So different lines are different perturbations. Here you see that there are two, Z1 and Z2, and essentially these are what I would be calling electromagnetic driven and gravitational driven. Essentially, these are the equations that reduce to gravitational and electromagnetic perturbation in Schwarzschild in the small RB limit. But for any finite value of the charge, everything is coupled. So actually, these are two perturbations which are coupled to each other. Okay, so this is the effective potential. Here is the black hole. I'm showing the charge to mass ratio here. Also here is the black hole with a different charge to mass ratio. You don't see anything special. This is the typical effective potential that you get for a black hole. It goes to 0 at the horizon. There is a maximum which in the larger limit corresponds to the photon sphere, and then it goes to 0 at infinity. It's the same for a Schwarzschild black hole in GR, in fact. The interesting part is in the topological star solution. So this is a topological star of the first kind, and what you get is that the effective potential diverges at R equal RB, actually diverges to positive values for all cases, but for this, the radial perturbation, so the type 2 radial perturbation in which it diverges at minus infinity. For topological 2 stars, instead, because of the unstable photon sphere that I was mentioning before, you get still this divergence at r equal to rb, and then there is a maximum here. So immediately you see that there is a cavity here that can support trapped modes and long-lived modes, and in fact this is what we will see. When we discovered that there was this negative diverging potential, we thought, okay, this must be pointing toward an instability, while, well, I will spoil this, and we search for unstable mode with INFN any. So they are all stable. Question?
I was worried too about that, whether that's an instability. What's the value of L for that?
So this is, well, it depends. The red is only for L equal to 0, because these are radial perturbations. They only exist for L equal to 0.
Yeah, because I've often wondered whether these topological stars have a sort of folding instability where they sort of, because they're not necessarily axisymmetric. So I've often wondered whether there is some kind of instability where they, one bubble collapses in a non-axisymmetric way.
Yeah. So the L equals 0 in this
No,
4D.
the L equals 0 is fine.
It's
That's not
fine,
folding.
Because this is 4D, but L equals 0 is essentially the scalar perturbation in 5D of the metric, right?
Okay. Yeah. Anyway, I was. So the other follow-up question I was going to ask at the end, which maybe comes later, is this going to be sensitive to any of folding instabilities, the analysis you're doing?
Yeah, well, I can tell you that we search for unstable mode with INFN any, both in time domain and frequency domain. I'll show you in a moment, but yeah. Okay. Yes, so essentially we have this equation here. It's a very simple second order differential equation. We can solve it numerically. There are many methods to do that. Let me start with solving it in the black hole case. In the black hole case, it's always a boundary value problem, but in the black hole case, the boundary condition is asking for purely ingoing wave at the horizons. And then you solve this problem with standard methods, and these are the quasi-nova modes that I was mentioning before. For type 1 L equal 1, for type 1 L equal 2, for type 2 L equal 0. I mean, as you can see, there are a lot of modes here just because there are a lot of degrees of freedom, which is why the problem is technically complicated. But conceptually, at least if you look at this plot, they are more or less the same. So this is the real part of the mode as a function of the mass the charge to mass ratio. Here is Schwarzschild. Here is actually up to extremality. Same thing for the imaginary part. I'm plotting the absolute value, so actually the imaginary part is negative, meaning stable modes. Okay, and the behavior is more or less the same. The only difference is that here in the type 1 L equal 2, you have two modes because there is the electromagnetic induced and the gravitational induced, but they behave very similarly. And this is the type 2 L equal to 0. In the black hole case, remember that the potential for L equal to 0 has nothing special, so we didn't expect any particular behavior here. In fact, these results are very standard. For a Raser-Nostrom black hole, you will see something very similar in principle. The things become more interesting probably in the topological star case. So here the only difference is that the background now has RB bigger than RS, and as was mentioned before, this means that there is no horizon. The 4D solution is singular, but we know actually what boundary conditions we have to impose because we know that the 5-dimensional solution is regular. And in particular, there is always an irregular solution near r equal to rb of the Schrödinger-like equation. So you can select the regular solution, and this automatically tells you that the 5-dimensional perturbation is also perfectly regular. So we know exactly how to solve this problem. There are no actually approximations here or like numerical artifacts, which is interesting because it's one of those cases in which it's true, it's still linear perturbation, it's not fully nonlinear, but it's one of those cases in which symmetries helps you to fully solve the problem, even if the background solution is singular. I'm showing here the sort of big picture, but well, you cannot tell much from this plot, so let me just zoom a couple of results. So the first one is this. These are type 1 L equal 1 perturbations. So this perturbation is a single dynamical mode, the electromagnetic mode. Well, here you see another interesting feature of this model, that we are just changing the charge to mass ratio, but changing this parameter interpolates smoothly between first and second kind topological stars. And here is the real part, here is the imaginary part. Here we are considering two modes. N is the overtone number, so n equals 0 is the fundamental mode, n equal 1 is the first overtone. Interesting enough, well, overtone and fundamental modes are distinguished in terms of the imaginary part. So the one that has the smallest imaginary part has the longest time scale, and therefore is the fundamental mode. And as you can see here, it might not happen, but it happens, that whatever is fundamental in any of these points of the parameter space remains fundamental. So the green here, the solid line is always below the dashed line. There is no crossing. And the other interesting thing is that, as you can clearly see, this is a logarithmic scale. The imaginary part is of order, say, unity, or anyway 0.1, or anyway it's of order of the real part in this region of the parameter space, so for first kind topological stars, which is exactly what happens for ordinary stars. These, in the literature of neutron star modes, they are called W modes. These are the gravitational modes of the star that exist just because it's a relativistic object, and they are in fact very similar to black holes. But as you change this parameter, you move on the left, this becomes more compact and interpolates between a star-like object and an ultra-compact object with a unstable photon sphere, and also a stable one. And this is shown by the fact that the imaginary part becomes very small. So these modes become long-lived because the time scale goes like 1 over the imaginary part, so the time scale for this becomes way bigger. And well, coming from a different community, it's very nice that a single model interpolates so clearly between one phase and the other. This vertical line is the transition between the first and second kind solution, and you clearly see that there is also this transition in the modes.
Topological stars don't have horizons, but nevertheless they have quasi-normal modes with an imaginary part.
Right, because of the dissipation at infinity.
At infinity.
Right. Yeah. This is the same. Neutron stars have the same property. These are called the W modes of a neutron star. Because these the boundary conditions at infinity are outgoing waves.
Yeah.
It's just that at the origin it's regularity instead of being ingoing. So dissipation here is only, if you put this in ADS, it will be normal modes.
You asked the question.
So you're saying that at R equals RB, there are no ingoing boundary conditions, it's just regularity. But when I looked at your effective potentials, it seems that they allow either for perfect transmission to the topological star or a perfect reflection. So I would have expected that either there is a complete ingoing wave or completely outgoing wave. So
yeah,
how do you reconcile?
I have to say I didn't look into the details, but I think that on physical ground it should be completely reflected. And essentially this is because these are 1D potential. So being completely reflected just means that that the wave goes through, well, I mean, think about a star, the same potential will happen for a star. And if the star is perfect fluid, it does not interact with gravitational waves, so the wave just goes through the star. And in terms of 1D means that it's reflected, but in fact it doesn't interact.
It's probably possible to show analytically that the regularity condition is equivalent to total reflection.
Actually, yeah, it's something that we discussed with Alex at some point. We were essentially linking this to the requirement that the net flux is 0. I think we don't have conclusive results there, but physically it makes sense, yes. So there is no dissipation at the center, yes. Yeah, which is probably because you are not exciting the extra dimension, so there is no leaking in that direction. Okay, so this was for type 1 L equal 1, type 2 L equal 0, I believe. Let me see. Yeah, it's this one here. So these were the potential, the case in which the potential was negative. We searched for unstable modes. Actually, we believed that they should be there, but in fact, we didn't find anything. And the behavior is, besides small differences, very similar to the others. In particular, the real part, the fundamental mode is standard. The only difference is that this is the fundamental mode. The first, it goes down near extremality, but it doesn't change much. And the imaginary part is also positive. As I said, we searched for unstable mode, we didn't find anything. Of course, you might say this is just frequency domain. So what we are doing is looking in the complex plane whether we find solutions with positive imaginary part. The fact that we didn't find it numerically doesn't mean that they are not there numerically, which is why we also looked into the time domain analysis. So what we did is, instead of solving the equation in frequency domain, you keep your time dependence of the equation. So instead of having one-dimensional system of ordinary differential equations, now you have a system of partial differential equation, 1 plus 1. So it's very actually straightforward to solve. There are codes that you can write to solve problems of this kind, even in the coupled case. I'm not giving any details here about finite difference methods, but if you are interested, Alex is the guy who's working on this, and also you can refer to Helvi's talk before. Anyway, so we solved this equation also in time domain. And in the time domain is nice because if there is any instability, it will clearly show in the time evolution. So you start with some initial data that excites the mode, and then you leave your system evolve. If there is an instability, what you should see is that the signal, instead of going down, it should eventually grow in time. Even if you didn't compute the modes, you will see an instability just because of that. So we use the time domain also for another reason, and the reason is, in this model we can play with the parameters and have a situation in which the topological star has a very similar charge to the compared to the black hole. Of course, the mass can be the same, it's just a scale, but we can set the parameters, like in this case here, such that the charge to mass ratio is very similar. Actually, it can be arbitrarily similar. In this example, it changes just by a few percent, and you can see that the effective potential is actually very similar in the two cases. It's not exactly the same here near the unstable photon ring because of this small difference in the parameters, but the crucial point, the take-home message, is that asymptotically is the same, because asymptotically these solutions have the same charges. The only big difference is that while for a black hole it goes to 0 at the horizon, for a topological star of this kind, this is second kind, is actually diverging and create this cavity here. Okay? So in a sense, almost only the boundary conditions of your problem change. The effective potential is almost the same. What happens if you solve this equation in the time domain? Well, it happens what you would expect after a lot of work with ultralight compact objects in, say, more toy model scenarios, which is that the prompt ring down in time domain is actually basically indistinguishable between this black hole and this topological star for these parameters, just because the prompt ring down is governed by the shape of this potential around here. And because they are very similar, you get a very similar result. However, these long-lived modes that exist because of this cavity show up later on in the form of what is called gravitational wave echoes. And these are really just modes that are trapped here. They go back and forth. They cannot escape here at minus infinity because there is actually an infinite barrier, but they can escape toward plus infinity, and eventually they will reappear. So the take-home message is that there are cases in which the topological star in time domain, even though the modes are completely different from a black hole, rings in the same way as a black hole plus echoes at late time. And this is supported also by frequency domain analysis. So here what I'm showing here is an example of the modes computed in the frequency domain and also in the time domain with Alex code. Well, first you can see that the agreement is actually great. And this is the fundamental mode for the magnetized black hole, precisely this solution here. You see that the fundamental mode of the topological star this one here, has nothing to do with this black hole. So the numbers are completely different. This is 10 to minus 2, this is 10 to minus 9. There is nothing similar to this, and these are the first 3 or 4 overtones. We went on, they are all similar in this case, so 10 to minus 9, 10 to minus 7, 10 to minus 8. So there is no mode similar to the black hole one, and still, in the time domain, they just look the same at the beginning. Consider also this is a logarithmic scale. So if you look at this in a linear scale, the prompt ring down, the standard ring down that LIGO sees is basically the same. Okay? It's not the case for topological stars of the first kind. You see that for a topological star of the first kind, the fundamental mode is similar, qualitatively similar to that of a black hole. So the imaginary part is comparable to the real part, which is what you expect for the standard W modes of a star. Yeah.
Are the same as the one of the ring down? The frequencies are the same. Can I see that this is an echo? It's the same. It's just coming back.
Right. So more or less they are. The problem is that anyway the frequency gets reprocessed while doing the tunneling through the potential barrier. So the frequency content is the same. It's not exactly the same because each time it does the tunnel, it gets sort of filtered out somehow. But yes. And the time scale, what is more important is that the time scale between, say, this and this is really the time that takes light to go from here to here.
Okay, but then they are produced at the photon ring, not at the cavity.
They are produced, well, in the time domain, what we are doing is there is an initial data. So it evolves, it starts somewhere outside, goes in. So it's the photon ring that vibrates, and then part of the radiation goes in. In the black hole case, it just goes into the horizon. In this case, it actually goes back and forth, and occasionally.
But then they are not related to bound states in the topological stuff. From the cavity states that they are bound.
Well, eventually, this time scale here is basically this time scale here. So there is a correspondence between what you compute in the frequency domain and this. So this is the mode that survives at late time. So it's the fundamental mode for the topological star. What is more puzzling maybe is the fact that at this early time, they ring the same even though, so the mode here, the ring down mode, is not part of the spectrum of the topological star in the standard state perturbation theory.
Yeah, just I think it's actually part of the first black hole mode is also in the topological star. It's just the n equal 4 will be there.
No, actually, I cut the table because it was too big. We went up to n equals 7.
Like you see, like n equal 4, like all the gaps are 0.07. So n equal 4 will be like 52, 51. And the imaginary part will be 10 power minus 4.
I think we have it. They might be quite similar, but not the same. Yeah.
It's slightly different, but it's still kind of close. It looks very close.
Yes, I see what you mean. I'm not totally sure, though, that this is the reason why they ring the same, but because then the excitation factor might be different. Yes, there are other modes with imaginary part close to this.
It seems that there is one mode which has a very similar real part.
Real part, I can check. I have it. I can check it later. Yes.
So something that I find kind of surprising is that the echo comes fairly late because the mode has oscillated almost 20 times before.
This initial part is initial data dependent because it depends on where you put it.
But I think, no, I see the number of oscillations when it goes kind of...
you mean from here to here?
So that's about 15 times oscillations. Yes. 15 oscillations before the mode has had time to reflect. That's a lot. Is this because this is close enough to extremality so that you have a long throat?
Yes, so precisely. This plot is highly misleading. I was lazy. I didn't put it in tortoise coordinate, which should be what... because this equation here, this row, is a coordinate in which in the black hole case, you are at minus infinity. So in this coordinate, this cavity is huge.
That's of course, that's always minus infinity. But the fact that the bounds that it takes so long to bounce, then this means that probably you have something like that you're close enough to extremality. I don't remember what's the
Oh yeah,
extremality
actually you
bound.
are very close to the extremity is precisely the point in between, essentially.
Okay.
Yes,
Okay.
yes.
So that's
Yes, yes. Because I mean, this is the model. Only at extremality, close to extremality, you have both the black hole and the topological star solution with the same similar charge. Yes. Yeah, and by the way, sorry, just to finish this, this is consistent with the fact that this mode is super small imaginary part compared to the real part. It's because of that.
Do you happen to know the redshift between the flat space and the bottom of the?
I didn't compute it.
I guess it's 15 or so. Is that
Oh yeah, actually, yes. All right. Okay, yeah, so this is just to, Elvi already presented this. I just want to mention that all of this was actually very expected, and in fact is the same sort of phenomenology that we found a few years ago with Taishi Ikeda and collaborators, and also people here from Tor Vergata, where we were studying the ring down, this time of a test scalar field, so it was less ambitious, but of a background solution, one of those microstates that Joseph and Nick computed, which have essentially no spatial isometry. So we had to solve a 3+1 evolution, like Elvi was mentioning this morning. And here is the result. The first row is comparing the black hole case. Here we are starting with a spherical perturbation. The black hole is spherical, so everything remains spherical. In the microstate geometry case, the geometry itself is not spherical. So even if you start with a spherical perturbation, eventually you end up with something that can be dipolar or triangular, depending on your geometry. But as you can clearly see here from the time snapshot, at t equals 60m, in the black hole case there is nothing. In the other cases there is still perturbation going on, just because there are long-lived modes that survive. And in fact, this is the time evolution that we get. Is, as you can see, qualitatively is very similar. For a black hole, everything dies off, and there is nothing more. In the microstate geometry case, there is an initial ring down, which is similar to the black hole, followed by echoes and by a long-lived mode that survive much longer. The problem here is that everything is a mess because of mode mixing, so it's much more complicated to study this problem. In the topological star case, because everything is so symmetric, is also very simple. Plus here we had to sort of cure the singularity in a numerical way with an artifact, while in the other case we didn't need, precisely because of the symmetries. Okay, so let me spend a few words on the Gregory-Laflamme instability, since we talk about that. We know that black strings are unstable against fragmentation, and for magnetized black holes, this happens in this region of the parameter space for spherical perturbations. So this is L equals 0 perturbations with Kaluza-Klein momentum, K. Because the background is independent of the extra dimensions, you can Fourier transform and have an extra parameter in your model. The nice thing is that magnetized black holes are actually dual to topological stars if you do a double Wick rotation, which is this one here, that switches RS and RB and also Y and T, which means that, and this was discussed in this paper here, which means that just because there is a zero mode for a magnetized black holes, you expect a purely imaginary mode for a topological star in this regime here. Actually, this is wrong. Let me see. Yeah, here there should be a plus, greater 2, not a less 2. But this zero mode for the black hole with K different from 0, the standard Gregory-Laflamme mode, translate into a purely imaginary mode with K equals 0 for the topological star. So we looked for these solutions, and well, no surprise, we found those. So now the imaginary part is no absolute value, so this is positive. This means instability, and is an instability that is purely imaginary, and it actually exists, and it goes precisely to a zero mode when RB divided by RS is equal to 2. So this is precisely the instability that in this paper was anticipated just because of this duality. Well, we find it numerically, which is a nice check of our methods, and I think that Giorgio will discuss more in detail this also in the case when the frequency is complex. On this we'll discuss on Friday.
cannot fragment because of charge conservation.
Okay.
That's dual. I mean, in 5D, the magnetic charge is dual to a string charge, and that's conserved. You cannot break them.
Okay. I was thinking about
they
this.
clamp, and they
sorry?
will stabilize at some clamping.
Okay. Okay. Good to know.
It will be like a supersymmetric black hole for a while and then bounce on it. Right?
Yeah, it develop bumps.
Okay.
Yeah.
I see. Thanks. How much time do I have?
A few minutes.
All right. Well, I thought I had time to do this, but I didn't. Well, I will not mention type 2L = 1 just because it's still work in progress. Perturbations are more complicated and we are still working on it. On top, you see the black hole on bottom, the topological star. And, well, I mean, so far everything looks similar to what I just discussed. Do I have 2 minutes? All right, just 2 minutes. One slide on a work in progress with these people here, all in Rome, Fabrizio Corelli, Robin Croft, and again, Marco Melis. This is work in progress squared because, well, as you can see, probably will be out in 2024, hopefully, but not anytime soon. And, well, with this, I hope it's clear now that it's interesting for various reasons to study theories like this one here. So scalar field, Maxwell field, some no-minimal coupling. If instead of taking the no-minimal coupling as coming from undimensional reduction, I'm just taking this function here. And the reason is this function allows for scalarized black holes. So in this theory, both Raser-Nostrom black holes and hairy black holes with a dilaton scalar field exist if the coupling is bigger than this value here. And, well, long story short, you can compute the solution. In this case, it's numerical. You can compute the perturbations. In this case, they are axial perturbations because there is no parity mixing. They do not decouple from each other, so you have a system of two equations. And the interesting things, well, these are the modes, they are not that important, is that the effective potential that you get is actually very funny. Sometimes you see that these are black holes, only black holes. Sometimes you see that there is a maximum, but also another maximum. There is a cavity here, and you see where I'm going. In this case, you would expect to have echoes, or anyway a funny ring down, even for black holes, so even without different boundary conditions. The good thing is that in this theory, you can do simulations, because these are black holes. In Einstein-Dilaton-Maxwell theory is something even simpler than what Helvig showed this morning. And, well, based on linearized analysis, this is what we are showing, this is what we are getting. There are long-lived modes. The imaginary part is small. It's not that small because the cavity now is less efficient to trap the mode, but still, in time domain, still linearized analysis, we see that there are sort of echoes. They are less clear just because now the boundary condition is actually that of a black hole, but still they're present. But the nice thing is that all of this was linear. Now we can do nonlinear simulations, so really take two black holes and produce a black hole which in principle can ring like showing echoes. And I'm showing this simulation, and then I will close. So this is the collision of two hairy black holes in this theory. You see they approach each other. I don't know what this happened. You see they never get to each other, and the reason is that this simulation is still ongoing right now. So we don't know what is the end state. I mean, the end state will be a charged black hole, hopefully, but we don't know yet whether the signal will be similar to what we are seeing in the linearized analysis. But anyway, this is just to say that in these control settings, we can do simulations and possibly find something interesting. So stay tuned to see the results. Conclusion, well, I think that the main conclusion is, as Helvig said, we are now ready to explore the dynamics of black hole microstates. We need some probably simplifying assumptions, so we should start simple. We might need some clever idea, but still is doable. For sure, the linearized dynamics is doable, but in the future, we want also to do nonlinear stability and study the dynamics. So far, the phenomenology, even in more sophisticated models, is broadly consistent with what we expected from, say, toy models of exotic compact objects. But, I mean, we have to see and check for the full nonlinear analysis. Okay, thank you.
questions?
Do you have physics expectations as to why it is possible that the topological star is stable?
I actually don't, and I was expecting. Well, I mean, I'm very agnostic. I wanted, in fact, to see, especially, probably is what Nick was saying, when you start perturbing the metric, really in the gravitational sector, whether this remains stable or not. I have to say, I mean, so far, everything seems stable, but yeah, maybe people in the audience have a better argument.
Just going to make another comment. I was misunderstanding the example you were using. This one's very spherically symmetric. This one's probably not folding unstable like some of the other topological stars. So, Pierre, can you comment? What's holding this thing out? It's got a bubble of nothing expanding, but what's holding it together?
So it's like a bubble of nothing. So it's top of the hill solution. So if you perturb it, like. Yeah, it's like a bubble of nothing. So if it has a top of the hill solution, but here we put flux on top of that, which is a magnetic flux, and the magnetic flux is a contraction resistant term. So it's like you add on, like it's a top of the hill potential, but you add a contraction dependent term, so it creates another minima. So the flux is stabilizing, and if the flux is not sufficiently strong, which is what we see here, you don't get this minima there. And you are typically like a bubble of nothing guy. Yeah.
So in a sense, it's only stable when the flux is large enough. Yeah, I mean, in a sense, I think the expectation would have been actually opposite. I mean, I think Samir, a few years ago, he was arguing that, if you build non-supersymmetric solutions, which are supergravity solutions dual to coherent states of the CFT, they will decay, and the decay was actually matched very nicely in the JMR solution to Hawking radiation. So it's the same calculation which gives Hawking radiation, which was matched by Samir. So Samir had this expectation about, maybe 10 years ago, when you're doing this JMR, that all these things should be unstable and the instability is expected. They are semi-classical solutions dual to coherent states, and therefore they should be unstable, and that's what you expect from the CFT. So this would have been a feature, but somehow here they want to be more stable than. Sorry?
It's metastable, so it can still decay.
It can still decay, but locally stable. So.
But that's is that because these solutions are double weak rotations of the magnetic string, so then the absence of that instability is the double weak rotation of the absence of the Gregor-Laflamme unstable mode.
Yes.
So
but you can also calculate without doing double weak rotation. So Giorgio and we're doing so we can also.
Yeah, I mean you can do it in one, but it's just a double weak rotation of that stability.
So I suspect there's some effective potential here where it's a local minimum. So it will be unstable to some tunneling instability.
Yes.
But it's not like the other ones you've been building where you have these things strung along an axis where I think there might be a folding instability. But these ones I think are genuinely perturbatively stable, as essentially Paolo has shown.
Question, yeah?
For the unstable one, can you relate the unstable mode to some temperature, like radiation or anything? How is it unstable? Is blowing up?
We didn't think about it. I would say the only thing we know is this and how the eigenfunction look like, which I believe they peak near RB. I have to say we didn't look into that, but in principle we can try to see whether there's a relation.
Okay. Any last questions? No? Okay, well, let's thank Paolo again.
Yeah.